Hi everyone. In this video, let's look at what is a Rolle's theorem. As I said in the previous video, the Rolle's theorem is a special case of the mean value theorem. The Rolle's theorem says if a function f(x) is continuous on a closed interval and differentiable on an open interval ab with the function value f of a equals f of b, then there exists at least one point c in the open interval ab such that the derivative at this point equals 0. Okay, so from this definition, we can see why this theorem is a special case of the mean value theorem, because it has one extra condition, which is it requires the function value to be the same at these two endpoints a and b, right? And in the mean value theorem, we don't see anything about um, what will happen to the function at these two endpoints. Okay. Now, if the function value are the same at the endpoints, that means when I connect these 2 points, the second line I will get will be a horizontal line. So the Rolle's theorem, it tells us now between A and B on this curve, I can find at least one point, and at that point, the tangent line gonna be a horizontal line. In this case, that point is it's like here. So that is the C. Okay. Since these two straight lines are horizontal, so their slope are both equal to 0. So that's why f prime of C equals 0. Another way to think about this is okay, if we consider the slope of this red line, since it's given by this formula, right? And right now, because f of b equals f of a, the numerator is 0. So that's why the slope of this blue line is also 0, because these two are parallel. In this graph, we have we can find only one point where the derivative equals 0. Let me draw another graph. On that graph, we have multiple points. So if the graph or function looks like this, okay, again, at A and at B, the function values are the same. So in this case, we can find more than one point on the curve. One is here, and here, 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 here. So we have we can find 5 points, right? Okay. So this is a Rolle's theorem. Okay, before we move ahead, um, let's review the mean value theorem and the Rolle theorem. So here we have four conditions. The first one says the function value at f of a equals function value f of b. Second condition says the function is continuous on the closed interval. The third condition says a must be equal to b, and fourth condition says function must be differentiable on the open interval. So I want to ask you this question. To apply the mean value theorem, which conditions are needed? And to apply Rolle's theorem, which conditions are needed? All right. The answers are to apply mean value theorem, we want the function to be continuous on this closed interval and differentiable on this open interval. Since Rolle's theorem is a special case of a mean value theorem, so these two conditions must be satisfied first. And the third condition is um, then in the Rolle's theorem, the second line is horizontal, meaning that these two endpoints, they are on the same level. So function value f of a must be equal to f of b. Okay. Okay. Next, we look at one application of the mean value theorem. So the problem is like this. We are given a function and we're given 2 points, a and b, and we are asked to find a number c such that the derivative of that number equals f of b minus f of a over b minus a. So to solve for this problem, the first thing we need to do is we want to verify that the function it satisfies the conditions of the mean value theorem. In other words, we want to show that first the function f is continuous on the closed interval from a to b, and the function is differentiable on the open interval AB, because only if the function satisfies these two conditions, then the mean value, according to the mean value theorem, we can show that there must exist a number c such that at that number this is true. Okay. So after we can show these two conditions, after we can show that the function satisfies these two conditions, then the next thing is we want to find where this number. Now at this number, see, this is Suppose this is f of a and this is f of b. To find this number, this is like we want to find on this curve from a to b, at which point we can draw a tangent line such that that tangent line is parallel to this second line. So that will be the number C. Okay, let me use this example to illustrate this idea. So here we are given a function fx equals phi minus 4 over x. Phi minus 4 over x. And x equals 1 and b equals 4. So the interval we are given is from 1 to 4. Before we start finding the c, let's take a look at if this function satisfies these two conditions. Now, first, if the function is continuous on the interval from 1 to 4. Now, of course, if we can graph the function, then we can decide this by looking at the graph, right? Okay, now I want to talk about the case where we don't have the graph. Okay, we don't have the graph of the function, and we don't have the graph of the derivative. So how can we do this? Remember we said when a function is continuous, that means the function is defined everywhere on that interval. Okay, so when we talk about if a function is defined or not defined, we are talking about the domain of the function. Okay, we're talking about the domain of function. So to answer the question whether fx is continuous on the interval from 1 to 4, we need to consider what is the domain of this function. Since the function has a term 4 over x, we know if x equals 0, the function will be undefined. So the domain is from negative infinity to 0 and from 0 to positive infinity. Okay, now that means if 0 is contained on this interval, then the function will not be continuous. Okay, now because obviously 0 is not on this interval, since x equals 0 is not in the interval from 1 4. Therefore, fx is continuous on the interval from 1 to 4. Okay. Right. So this is the graph of function. Now we can say if we consider the number 9 from negative infinity to positive infinity, of course, this function is not continuous because the graph breaks here, right? But if we only consider the interval from 1 to 4, the graph is a smooth curve, right? Okay, so this is how to answer, how to check the first condition. Okay, just by taking a look at, by considering what is the domain of the function. Okay, now how do we know the function is differentiable on this open interval from 1 to 4 if we are not given the graph. In this case, because we said when function is differentiable, that means the derivative exists, right? The derivative exists. So we first need to know what is the derivative of this function. So we take the derivative of this function and need to find the derivative function, which is 4 over x squared, right? If you forget about this, because fx is a 5 minus 4 over x, which we can write as 4 times x to the power of -1. So the derivative of 5 is 0, and the derivative of the second term we can find it using the power rule. So minus 1, -1 minus 1, that's -2. So -4 times -1 is positive 4 times x to -2. That's why the derivative function is 4 over x squared. Now, if the derivative exists on the interval from 1, 4, that means this derivative function also exists on the interval from 1, 4. So the answer to the question still be the same. This time we wanna consider what is the domain of this derivative function. Okay, the domain of this derivative function is everything except 0. And because 0 is not contained on the interval from 1 to 4, so this derivative function exists on the interval from 1 to 4, and because the derivative function exists, the function is differentiable. On the interval from 1, 4. Because if it exists, that means no matter which number we plug in into this derivative function, we can always find a number, and that number stands for the slope, right? Stands for the derivative. Since we can find any on the interval from 1 to 4, we can find the slope at any numbers, and that's why the definition of a differentiable tells us the function is differentiable on the interval. Okay, so the second condition is also checked. Okay. So to check the second condition, we consider the domain of the derivative function. Okay, okay, so this is how we do if we are not given the graph. Okay, okay. Now, after we finish this, we can see that yes, the function satisfies these two conditions. So, according to the mean value theorem, we can find this number c. Okay, now how do you find this number c? So first, we need to evaluate what does this equal? What does the f of b minus f of a over b minus a? Since we are given the function and we're given what is a and what is b, so that is f of b is f of 4, and f of a is f of 1 over 4 minus 1. When x equals 4, since f of 4 equals 5 minus 4 over 4, which is 5 minus 1 equals 4. Okay. And f of 1 equals 5 minus 4 over 1, right? Which is 5 minus 4, which equals 1. Okay, since the numerator and denominator are the same thing, so this equals 1. So now the question is, we want to find the number such that at that number the derivative equals 1. So because the derivative function we already know is a 4 over x squared. So this question turns into, what is the solution of this equation when c equals which number? 4 over c squared equals 1. And this equation is very simple. So if we multiply c squared on both sides, we can find that c equals positive and negative 2. However, remember that our interval is from 1 to 4. So we have to drop the negative result. Therefore, c equals 2. Okay, c equals 2. Okay, let's verify this result. Okay, so when x equals 1, so first we have these 2 points. Okay, 1 f of 1 and 4 f of 4, right? These are the endpoints. Now let me connect these 2 points so we can have a tangent line. So the slope is 1, right? So if I use this point to graph this second line, so y minus the y value equals the slope times x minus the x value. So this is our second line, right? At 2, when x equals 2, let's see, if the tangent line at this point will be parallel to this purple line. So at this point, y minus f of 2 equals the slope is 1 times x minus 2. You see, right? So because these two straight lines, they have they're parallel, so they have the same slope. So that's why the derivative at this point when x equals 2, f prime of 2 equals it equals this. It equals the slope of this second line, which is given by this formula.